back in the Middle Ages, there were lots of people who tried to transform low-cost metals like lead into gold. And this was known as alchemy. And they were never successful because in a chemical reaction, elements retain their identity. You cannot turn anything into gold in a chemical reaction. So, doomed to failure, but they didn't know that. In a nuclear reaction, though, you can change one element into another element. This is called transmutation, the transformation of one element into another. And this happens in all types of nuclear reactions. Radioactive decay, which we talked about at the beginning, fission, the splitting of the atom, and also in fusion. So you start with one or more elements, and you end up with different elements. There's a couple of nuclear reactions that can result in transmutation. Nitrogen-14 being hit with an alpha particle can turn into oxygen. Aluminum-27 hit with an alpha particle can turn into phosphorus. So it is possible to turn other elements into gold. Is it financially worth doing? No, absolutely not. You'll be better off going out and hunting for gold in the dirt. Well, how do you, say, take nitrogen and hit it with an alpha particle, right? Back in the 1930s, scientists began building devices to accelerate particles to high velocities. It's like, how can we take a particle and accelerate it, essentially throw it extremely fast at another particle, and try some different transmutation reactions? We're throwing particles at elements and just seeing what happens. So there's a couple of different devices. One is a single-stage linear accelerator. So here you have a charged particle that gets accelerated in an evacuated tube by a potential difference, a voltage, between the ends of the tube. So you have, say, a positive particle, you have a positive charge at the end where the particle begins, and a negative charge at the other end, and so that voltage difference causes the particle to accelerate. The Stanford Linear Accelerator is a multi-stage linear accelerator. Instead of just one voltage difference, there's a whole bunch. And this allows particles to be accelerated up to 90% of the speed of light, which is really, really, really fast. This is a photograph of it from an aerial photograph. It's really long. So when these particles collide with a target, they're going to produce a shower of subatomic particles that can be studied. And so they're literally throwing particles at stuff and just seeing what happens. And lots of interesting things happen. So one of these things led to the Nobel Prize in Physics for researchers using the SLAC. They discovered that protons and neutrons are composed of smaller particles. Those smaller particles are called quarks. So, in chemistry, we talk about the subatomic particles as if they were indivisible, right? Protons, neutrons, electrons, right? They just are what they are. Well, now we've seen that protons can turn into neutrons, and neutrons can turn into protons. And these experiments show that the protons and neutrons are actually made up of smaller particles themselves. So then you start wondering, well, how far does this go, right? So this is how the multi-stage linear accelerator works. You've got a series of tubes of increasing length, and they're connected to an alternating voltage. So here we have the proton source, and it comes through the first tube. It comes through here. So initially this number 1 here is going to be a negative charge to attract the proton. And 2 is going to be a negative charge, initially this is negative to attract the proton. As the proton comes in here, it switches to positive to push it away. The next one's negative. When the proton gets here, it switches to positive. And so the voltage here is going to alternate. It's very sophisticated. But in this way, you can get the proton to go faster and faster and faster until it hits the target. So that's a linear accelerator. You can also have a cyclotron, which is circular. This is a picture of Fermi National Accelerator Lab. It has two cyclotrons. So there's one here and another one over here, arranged in a figure-8 configuration. So here what happens is the particle, the proton, is going to go in a spiral. And so we have voltage sources on each semicircle, each half of the circle, and those will alternate. And as the proton gets larger and larger and larger in its circumference of travel, it will go faster and faster and faster until it hits the target. And again, what we're talking about here is just, scratching the surface, just trying to give you an idea of what kind of things are out there, right? I'm not going to test you on the mechanics of a cyclotron, right? But a cyclotron can be used to accelerate a particle.